This is a program about geometry, the geometry of the real world, the geometry of space and time. Well, up to now, you've just been used to the geometry of space. In Euclidean geometry, we can represent a point by its three coordinates x, y, z in free space. And then when we transform to another coordinate system, we transform x, y, z to x prime, y prime, z prime. But in the geometry that we're concerned with today, we have to introduce a fourth dimension, time. That's because we're interested in the geometry of space and time. So x, y, z, and t transform to x prime, y prime, z prime, and t prime. Well, it's not at all clear that it's really necessary to transform t. Surely all we have to do is synchronize our watches, and then we'll all agree about the value of t. Well, is that the case?
That's an intriguing question, and funny things do happen with time in real life. This is a spark chamber, and it's used for detecting muons, that is, elementary particles from the upper atmosphere. Each time particles arrive here on Earth, the chamber sparks. When we filmed this, we lowered the outside light so the sparks would be more visible. Now, the funny thing is, there just shouldn't be any sparks, or hardly any. The muons they're detecting just shouldn't be getting here. The muons themselves form in the upper atmosphere. What we know about muons is that they should live for about 2 microseconds. That's 2 millionths of a second. And we know that from experiments with muons in the laboratory. So with the speed at which they're traveling, we wouldn't expect them to get much beyond the upper atmosphere. But in fact, they do reach us here at the Earth's surface. And to do this, they must live for about 30 microseconds. So what's going on? The only difference we can tell between cosmic and laboratory muons is their speed. Cosmic muons, detected by the spark chamber, are traveling at speeds approaching the speed of light relative to the Earth. In fact, they're traveling at 99.7% of the speed of light. What can we make of that? A muon that should, on average, live for 2 microseconds survives for 30. The faster muons seem to have a much longer lifetime. There's no scientific reason for us to suppose that the muons are different in nature, so it looks like we have a problem of time. What we measure as a lifetime seems to be 15 times longer than what the muon measures as the lifetime.
So it seems that for us, the muon's lifetime is stretched. The value t that we measure is 15 times greater than the muon's t prime. Well, that's an absolutely incredible effect. Time seems to be stretched, dilated. Why didn't anyone notice that before? Well, Jeremy gave us the clue. It's all due to the fantastic speed at which these muons are traveling, almost the speed of light. It turns out that these effects are only noticeable at velocities approaching light velocity. So, to analyze these effects, we've got to analyze the speed of light. Well, what is that speed? It turns out that Galileo was one of the first to consider that it might even be finite, and though he tried to measure it, well, his methods were just too crude. Now, with modern technology, we can do a lot better, and that's what I did when I went to the University of Paris. This is a light source. It sends out pulses of light. Well, you can see them in this piece of paper. Each time it pulses, the light hits this light detector. And precisely 3 meters along, a second detector. And each detector sends out an electrical signal which is registered as a peak on the oscilloscope. And the distance between the peaks gives me a measure of the time interval, the time it takes the light to travel from this detector to that detector. And when I divide the distance by the time taken, then I get the speed of the light. Here's the signal from the first detector.
And here's the one from a second. And the space between the signals represents the time interval. Well, on this time scale, the interval is 10 to the minus 8 seconds. So that means that the velocity of light is 3 meters divided by 10 to the minus 8. That's 3 times 10 to the 8 meters per second. Well, that's a pretty good value. It's very near the accepted value, and we represent that traditionally by the symbol c. Well, it's a fantastic velocity. It means that a pulse of light would only take about a 500th of a second to travel from London to Paris. Well, the fact that it's fast is interesting, but it's not all that interesting. What is more surprising is the fact that this c turns up in all sorts of different physical contexts. X-rays, radar, radio waves, elementary particles. And that led Einstein to make the very daring suggestion that c is a constant for everyone, a universal constant. Well, why is that a daring suggestion? Well, supposing I myself am traveling along at nearly c, and I emit a light beam, which will go at c itself, you as an observer might expect to see the total velocity as being 2c. But in fact, Einstein says no, it'll still only be c. Well, this non-additivity of velocities would probably not show up at everyday speeds that we're used to. But physicists go to great trouble to make elementary particles travel at very high speeds, almost approaching c. And that's one of the reasons that we've come to this laboratory at Orsay near Paris. The particles they use are electrons. From this control area, they start them in motion. The electrons travel along this linear accelerator and get faster and faster, passing along this tube until they finally arrive at this storage ring where they circulate at speeds approaching the velocity of light. Well, to understand a bit better what's happening, take a look at this model. The electrons travel around the ring in groups. As each group turns the corner of the ring, it emits a pulse of light. Well, the light comes out here. It's detected by this detector and by this second detector precisely 3 meters away, just as in the previous experiment. And we can actually see the effect of the light being detected on this oscilloscope, where here we can see the pulses. We notice that the peaks are exactly the same distance apart. And that means that the light in this experiment is traveling exactly the same speed as the light in the previous one, even though they're being emitted by electrons, which are themselves traveling at almost the speed of light. So it appears that Einstein was right. In the velocity of light, we have a truly universal constant, and no other experiment has ever shown otherwise.
Okay, all the evidence tells us that the speed of light is constant for all observers. But how's that going to help us unravel the problem of time transformations? Well, we're going to follow Einstein's approach and just think logically about the consequences of this property of light. But of course, the first problem is that this speed is so unimaginably vast that we have no feeling for it at all. So what we're going to do is pretend that the speed is just 1 meter per second. And with this new slowed down light, we can carry on thinking about the way space and time would be. And it isn't really just whimsy, it's very much the way Einstein did it. We've already seen how to measure the speed of light. This is what it would be like with this new slowed down light. Here's the source that I have, and I'm going to shine light down the other end of this table and back, because there's a mirror there. It's a total of 4 meters, because it's 2 meters to the mirror, 2 meters back again. And of course, at 1 meter per second, that should take 4 seconds. So let's see. There you are. And that's what we'll do. We'll imagine light behaves as a scaled-down copy of the real thing.
So we think of Jeremy always moving relative to me with a constant velocity approaching our speed of light. So if he's going at, say, 0.6 meters per second, that's 60% of our speed of light. So he's behaving just like the muons in that experiment, and they were also going very fast. So if there are any time measurement effects, then at that speed, we really ought to be able to detect them. So how can we detect them? Well, Jeremy starts his clock when the light leaves his lamp, and he stops it when the light gets back. And in that time interval, which Jeremy measured as 4 seconds, he was moving relative to me from left to right. Well, actually, this is the direction along which Jeremy was moving, and I've marked the spot where he was when the clock stopped, and I've also marked the spot here where he was when he started his clock. So let's measure that distance. Well, that's precisely 3 meters. Now, the light actually hit the mirror when the mirror was here, and I marked that spot too, so I can measure that. 1, 2, and that's 2.5 meters. So the round trip that the light made, as far as I can tell, was 2.5 plus 2.5, 5 meters. The light traveled 5 meters at 1 meter per second. Now, both Jeremy and I agree that 1 meter per second is the velocity of light, so the light must have taken 5 seconds. But Jeremy got 4 seconds. Now, why do we disagree? Well, clearly we disagree because we agree about the speed of light. The reason that we get a time disagreement is because we have a constant speed of light. Now, we can get rid of the time disagreement if we abandon that concept. But the constancy of light is a well-founded experimental fact, so we're going to hold on to it. Now, what is the event that we're measuring? We're measuring the time between two events, in fact, between when Jeremy and I started our clocks and when Jeremy and I stopped our clocks. Well, Jeremy's clock is running slow relative to mine. His seconds are longer. In fact, Jeremy's time is dilated. What he calls 4 seconds, I measure as 5 seconds. In fact, in general, it's fairly easy to get a formula for this time dilation effect. And I'm going to do that now. Well, t is the time I measure as Jeremy is going from here to here with velocity v. So the total distance from here to here is vt. And this half distance is just vt over 2. Now, the speed of light in general will use the symbol c. So it's t for this distance. ct is the whole distance it goes. And this arm is simply ct over 2. Now, what about that? Well, that's just the distance from Jeremy to his mirror, and that's L. So now we have a right-angled triangle. We can use Pythagoras, and I get ct over 2. The square in the hypotenuse is equal to sum of the squares on the other two sides. Now, what am I looking for? I'm looking for an expression involving t, so I can take t squared to the left. Well, I can take the square root and get t, and it simplifies quite nicely. I'll get 2L divided by c all over the square root of 1 minus v squared over c squared. Now, 2L over c, what's that? Well, that's just what Jeremy called his t prime. So I can put this equal to t prime, and I get my final result. T is equal to t prime divided by square root of 1 minus v squared over c squared. That's a nice little neat formula. And in fact, when v over c is 60% of the velocity of light, as it was for Jeremy, and you put 4 seconds in here, you'll get 5 seconds out here. So, in fact, that checks with what we got before.
Well, now perhaps you can understand more fully why there was that apparent contradiction in the muon experiment. The cosmic muons travel at 0.997 of the speed of light, which gives a time dilation factor of 15 using the formula that Alan's just shown you, and you can check that after the program. So, what we measure as 30 microseconds, the muons only measure as 2. And that brings us back to our original question which Alan asked. You've seen that it really will be necessary in this geometry to do transformations that involve time as well as space coordinates.
Now, in the rest of the program, we want to explore the transformation between Jeremy's coordinate system and mine. Now, we know we have to transform t, time, so our system is really four-dimensional, space plus time. Well, it's a bit difficult to visualize 4 dimensions, so we'll simplify to 2 dimensions, one space dimension x and one time dimension t. This is my x-axis, and this is my t-axis. And a point here, for example, this point 3, 5, is just an event that occurred 3 meters away from my origin and 5 seconds after I started my clock. I'll write it 3, 5, because that makes it easier to act on with a matrix. Now notice I used the word event. That's the technical word for a point in space and time. Now, what about a curve? Well, that's just the trajectory of a particle moving along in space and time, and the technical word for that is world line. Now, of course, I'm stationary with respect to my coordinate system at the origin, so my world line is simply the t-axis. Now, as Jeremy goes by me, my clock starts, and I can describe that event with my space-time coordinates. So you can see what his world line looks like in terms of my coordinate system. Light with speed 1 meter per second will have a world line like this. And we can compare Jeremy's world line with that.
I could tell a very similar story to Alan. Here's my space axis, which I've called x primed, and my time axis t primed. I've called them x primed and t primed to distinguish them from Alan's coordinate system for space-time, which he's called x and t. And here's the world line through the origin of a flash of light. Call it a light line. Now, Alan and I agree to have the same origins for our different coordinate systems, and when we do that, this light line is exactly the same in my system as the light line in his. And since light in both our systems travels at 1 meter per second, this line bisects the angles between my axes and the angles between his.
That's just the clue we needed to link Jeremy's coordinate system to mine. You see, once we've agreed a common origin, then we have the same light line bisecting both our axes. Well, this is just Jeremy's world line, so that's his t prime axis. And this is his light line, the same as mine, and that must bisect his axes, so this line must be his x prime axis. And so we see that Jeremy's orthogonal axes have been transformed into a pair of non-orthogonal axes.
Well, again, I can tell a symmetrical story. Alan moves in this direction relative to me, so this must be his time axis, t. The common light line we have bisects his axes, so if I copy the angle, I must get his space axis. Let's call that x. Now, one event you've seen already is this one, the event of the light returning to me 4 seconds after it left. I haven't moved, so the space coordinate must be 0. The light took 4 seconds to go there and back, so the time coordinate must be 4, space-time coordinate 0, 4.
Well, the event Jeremy called 04 is just the one I've already called 35. And you can see that it's on his t prime axis. So the event Jeremy called 04, I call 35. 04 gets transformed to 35, or more generally, x prime t prime gets transformed to xt. Well, in order to find out a bit more about this transformation, let's embark upon another imaginary experiment. Imagine I'm situated with a mirror placed x from me. As usual, I observe Jeremy going by. A pulse of light also passes me at time t1 and then passes Jeremy. The light pulse then hits the mirror at time t. On reflection, the light pulse then passes Jeremy again and then me at time t2. Now, the event we're interested in here is the light pulse reaching the mirror x away from me at time t. So I could ascribe space-time coordinates xt to that event, and I could calculate those from my time measurements t1 and t2. So let's look at that again. We'll do it in terms of the space-time graphs. Jeremy's world line will go through my origin as before, but now look at the times t1 and t2 and the event xt. During that, I'm only able to measure time with the clock next to me, that is time on my world line. That is the origin, T1 and T2. And from those measurements, I can say something about the event xt, that's the distance x from my origin, at a time t after I start my clock. Now, this distance x has the same magnitude as this time interval. That's just t minus t1. Rearranging that equation, t1 becomes t minus x. In a similar way, the magnitude of x is also equal to this time interval. That's t2 minus t. And rearranging this equation, t2 becomes t plus x. A connection between the time measurements t1 and t2, which we're going to use, is given by their product t1, t2. That's t minus x by t plus x. Well, that's just t squared minus x squared. And this relationship is going to help us establish the nature of the transformation between mine and Jeremy's space-time coordinate systems.
That's right. I can tell a symmetrical story to that one, except the mirror is moving relative to me, and I get a similar graph to give this result. T prime squared minus x prime squared is T1 prime, T2 prime. In my graph, this is where the light first passed Alan, T1, and where it came back, T2. In his graph, this is where the light first passed me, T1 primed, and where it came back, T2 primed. And this, xt in his frame, and x prime t primed in my frame, is the same event, the event of the light hitting the mirror and setting off back. What we find is that for the same event, the quantity t squared minus x squared is equal to t prime squared minus x prime squared. That's what we're going to prove now, and it's done very simply by similar triangles. We're going to see that this triangle with T2 and T2 primed in it, let me just slide this in, T2, T2 primed, is similar to the little white triangle here with T1 primed and T1 in. The little angles at the base are equal, the big angles are the angle between a light line and the vertical, so they're equal. The two triangles have the same angles in, so they're similar. And if I look at corresponding sides, I get the ratios are the same. T1 primed over T1 in the little triangle is equal to T2 over T2 primed. In the big triangle, clear of fractions, I get T1, T2 is T1 primed, T2 primed. These expressions are equal, and so these expressions, t squared minus x squared and t prime squared minus x prime squared, must be equal, which is what we want. And that's what we need, a connection between my x prime t prime and Alan's xt space-time coordinates.
That's just what we wanted to know. The transformation from Jeremy's coordinate system to mine preserves the form t squared minus x squared. It's a bit like Euclidean rotations which preserve x squared plus y squared. Now remember, we used 1 meter per second for light velocity. If we use c, then the form that's preserved is c squared t squared minus x squared. And the matrix which preserves it looks just like this. You'll probably recognize the terms in the leading diagonal as those which gave us the time dilation factor. And this matrix acting on Jeremy's coordinates give the event specified in my coordinates. This transformation in the four-dimensional case contains the essence of Einstein's special theory of relativity. It not only gives us those time dilation effects we've already discussed, but also length contraction, and even forces us to reconsider our ideas of simultaneity. A non-intuitive geometry, maybe, but nonetheless, the real geometry of space and time.